This is section 4, rates of change. So now we're going to look at what a rate of change is and how that applies to math. And you've talked about rate of change before. Typically when you talk about the slope of a line, you're talking about its rate of change. Normally over time, right? And so when we're talking about rates of change, we really want to find the rate of change of the tangent line. Now, when you were in geometry, you learned that a tangent line is when a line touches a circle exactly one time. Okay, so if you look at the picture over to the left, this straight line that P is on is a tangent line. But that's not how we're going to make this a little less limited of a concept. Okay, so we don't want to just think about tangent lines and relationships to circles. We want to look at them as general curves. So let's look at what is and is not a tangent line definition, because there are a lot of misconceptions out there based on this idea of the tangent line just touching the circle one time. So here are a bunch of ideas that people come up with. So the first misconception is that a tangent line crosses the curve at one point, and that's not true. Okay, it can cross the line, but it doesn't have to. It's possible that it can just brush up against it. And if you were looking at this function and you were coming up with a tangent line, it would actually be like that. Excuse my curvy lines, sorry. All right, and so it does matter where it crosses the function, okay? And it doesn't have to cross the function at all. Misconception number 2, a tangent line to a curve must cross the curve only once. See, if you look at this, that's wrong, because the line on that contains the point P, that straight line, that is the tangent line at that particular point. And so what we normally do is we only look at the tangent line in a very small window. Okay, so instead of thinking about it as, oh, it's this really, really long line, we're looking at very short lines, okay? And we're worried about what they're doing, what that slope is. Another misconception is that a line is tangent to a curve if it touches the curve at one point but does not cross the curve. And so this example would be another one where you can see that line that you're looking at touches the curve, and it doesn't cross the curve, but that's not the tangent line. The tangent line would actually be more like that. Okay, and then the fourth misconception is that a tangent line to a curve is a line that just grazes the curve at one point but does not cross the curve. And just like we saw with misconception 1, it can cross the curve. It just depends on what's happening on the curve. Now, we'll come up with an actual definition of a tangent line later, but for now, we're just going to look at what tangent lines would do. Okay, so for each equation, draw the tangent line at the indicated x value. The x value that you pick is important. It does change what the tangent line is going to look like. Now, your goal when you're drawing a tangent line is to follow the curve. Okay, so if a curve's going straight up and down, your tangent line is going to go straight up and down. If your curve reaches the top, then your tangent line is going to be horizontal. So, for instance, this is just so you can see it, right? But if I'm looking at B, I'm not choosing A because A is linear, and I'll show you what that is in a second. But if we're looking at B, the tangent line over here would be like that, and it follows the curve as you move from left to right. So at the top it's flat, and it kind of follows it down. So we're imagining a bunch of little bitty lines that form the shape of the curve. So if you were only given the tangent lines, you would be able to come up with the curve. Okay, the slopes. If you were only given the slopes of the tangent lines, you could actually come up with the general curve. And we will actually do that later on in the year. So for now, let's just identify what the slopes are, those particular values. So for A, we're looking where x equals -1. Well, -1 is right here. Okay, because if you look at the scale, it's by 2. So If I were to draw the slope, the tangent line, because it's linear, it actually lies right on top. And that's the tangent line. Okay, and that's going to happen anytime it's linear. So, interesting thing that happens. Part B is asking for x equals 0. X equals 0 right here. Well, if you follow, right, we've got this line and this line and this line and this line and this line, and we keep going until we get to the top. At the top, it's horizontal. So that is the answer. So let me get rid of these. For C, we're looking where x equals 1. Well, x equals 1 right here on our graph. So if I were to follow this one, I'd draw stuff like this, and then get less steep, and then it'd go straight across, and then back up. And it'd get steeper and steeper and steeper, right, as we go. So that is the answer, because that's where x equals 1. All right, for D, we're again looking where x equals 1, so let's look right here. Okay, and I'm going to draw a bunch of little tangent lines. So just going from left to right, I'm just going to follow the curve. Right, if I had something like a toothpick, that would follow even better. Well, that's going to look something like that. And if I were to continue, so it's that right there. Okay, kind of just brushes it. Now let's look at E. Well, x equals 3 is right here. All right, so if I'm going from left to right, I've got this, right? It's a linear, so it's actually going to be the line. And then to the right, it's going to be that line. However, when you have something like this corner, because it's not smooth, the tangent line actually does not exist. So you're actually going to write none. No tangent line. And that's okay. For F, we're looking where x equals 0. That would be right here. And so if we go, and we kind of follow, there we go. And keep going up. So this answer would look like that. It'd be a little flat right there. For y equals sine x, let's look at pi. Pi is right here. And so if we go up, at the top it'd be flat, and we keep going down. At the bottom it'd be flat, and following the line. Top would be flat, and then that would go straight through. So there's your answer. At 4, this is interesting. So if we follow it, it gets more steep as we go. And then because it's steepening out there, and that's actually where our domain stops, it's actually vertical. So that is a vertical tangent line. That does exist. You can have a vertical tangent line.